Hi guys, this is Mrs. Gastler, and in this video we're going to talk about using energy bar charts. Energy bar charts are kind of like energy pie charts, but instead of showing like a relative ratio, they show actual amounts. Now with the pie charts, we're always looking at a closed system and the total remains the same, which is why the circle remains the same size. In a bar chart, we can talk about energy that comes in and leaves, or we can talk about energy that stays the same. So in this first example in your book, we've got a ball going up and back down, and we see that the kinetic energy gradually turns into gravitational potential energy and then back to kinetic energy. And we show that in the bar graph by starting out with all of it as kinetic energy, and then it is about half and half, so the same amount. See how there's some lines here to give you an impression of an amount. Kinetic and gravitational potential energy, and then we've got them going back. So it's the same idea, we just are saying how much energy there is. In this situation, the system is closed, so the total still remains constant. If I were to stack that bar on top, I would still have the same amount. In this example, here we have a spring, and we have three kinds of energy you can see here: the elastic potential energy of the squished ball, the gravitational potential energy of it being up off the ground, and then the kinetic energy. It's not moving here. It starts moving and we unstretch it, we let it go, so the elastic potential energy goes away. And the gravitational potential energy is going up because it is higher than it was. And now here it's stopped all the way at the top, so there's no kinetic energy. It's not touching the spring anymore, so there's no elastic potential energy, and it's all the way at the top, so it is the gravitational potential energy. Here, this one is also a closed system, because if we stack all these up, we're going to end up with the same amount of energy every time. So sometimes, there's this last example here, sometimes the energy comes in or goes out, and so here we have a box and earth, and someone is pulling the box up. So someone is giving this box energy. So you'll notice that we start with kinetic energy and gravitational potential energy. It's up off the ground, and it's moving upward. And then over here, it's up off the ground even more, but it's moving upward the same amount because it's being pulled. So what we show in this circle in the middle is that energy is going into the system. Okay, this one says work exterior. That's what that means. You do work when you give something energy. Okay, you can also do work to take energy away, but we're saying that work is happening here to put that energy into the box to make it go up higher. Last example here, we've got the box being pushed by a spring, okay, and it is stretching it out. There's a force being pushed on, or applied to the box as well. So here we are doing work on the system again, and we start out with no energy because it's just there, and as we move it to stretch it out, it's also on a rough surface, so there's some thermal energy as well. We're doing work on it. So you see it didn't have any energy to speak of to begin with because it wasn't moving, it's not up, it wasn't stretched. And now it is moving, okay? It is stretched, and it's also heating up because of friction. So that's what's happening. That's how we draw these bar graphs, okay? So we're just showing a change. So we always have a beginning and an end to show the change. And that's all the examples. Yes, okay. So we're gonna do this one together. Okay, this is the next worksheet, converting energy pie charts to bar charts. It has a number in Schoology. I don't remember what it is, but that's okay. And so what we have here is a wind-up Volkswagen toy car. It's set on a tabletop, and a spring unwinds as the car goes faster, at a faster speed. It says we're not including the tabletop. Okay, so that either means that there's no friction, but I don't see anything to tell me that there is no friction. But I am also looking at it going up to its fastest speed. So if I were to draw a picture, it would look like this. There's the car, and then it's going, okay? And so we want to think about what kind of energy it has. Well, at the beginning, it's wound up, and it's just sitting on the tabletop. So the only energy that it has is elastic potential energy, okay? As the car begins to move, that elastic potential energy is transformed because the energy turns into something else, okay? Now that's something else that the energy turns into is kinetic energy. So that's how I know it is transformed. If it went to a different object, it would be transferred, but right now it's just transformed, okay? So if I were to show this in a pie chart, I would have elastic potential energy to begin with, which I'll pretend that one's white. Look, I colored it in already. And I would have kinetic energy to end with. And so I'll have dots over here. Okay. In a bar chart, I would show it like this. So here it's showing me my system. So this is my opportunity to show the energy is coming in or going out, depending on the situation. And here we've got, oh, those are the wrong labels. Did I really not fix those? It's fine. Oh no, that's terrible because it's got the thermal there. Poo. It's fine. Okay. I don't have any gravitational potential energy. I don't have any kinetic energy in the beginning, right? This is the initial spot. And I have all elastic potential energy. So I'm going to draw my bar on elastic potential energy. May need to label some of these. So when you see this, this sheet is a little outdated. When you see PEG, that is gravitational potential energy. When you see KEM, that's kinetic energy. When you see PEEL, that's elastic potential energy. And when you see KETH, that's thermal energy. You can just remember that. That's an older system of labeling, and it's fine, okay? So my elastic potential energy is turning into kinetic energy, so I'm going to draw that right here, like that, okay? And so that's it. That's my bar charts, and that worked out pretty well because I didn't have any energy coming in or going out, and so showing it on my pie chart was pretty easy. So here on this next one, this one is going to throw us a little bit of a loop here, okay? We've got a ball that's on a compressed spring. It is going up, leaving the spring, and then stopping at the top, okay? So if we think about the energy transfer, we have some elastic potential energy that is turning into some kinetic energy and some gravitational potential energy at the same time. Gravitational, and then it's turning into all gravitational potential energy, okay? So that's what we're going to see in our bar graphs and in our pie charts. So when we consider the ball, the spring, and the earth, that's everything that we need to be able to consider all of these things. So this is a closed system, and the reason we know this is because all objects are included. Okay, there won't be any energy that's going to be unaccounted for in this situation. So in my closed system at the beginning, I have elastic potential energy. And at the end, I have gravitational potential energy. So when I do this, I can fill in all of my pie here. So it's all gravitational there, okay? Now, this one says, how would the bar chart change if we took the spring out of the system? Okay, what does taking the spring out of the system do? Well, the thing that is stretched or squished is no longer in it. So that means that there's no elastic potential energy for me to consider. So when I draw this, my first pie would be non-existent because I don't have anything stretched. And I can't draw that with a pie. I can't have an empty pie chart. It doesn't work that way. So that's why drawing a bar chart is necessary. So initially, it's not moving, okay? So there's no kinetic energy, and it's not up, so there's no gravitational potential energy. Well, if I considered this, maybe there is a little bit. We can do that, okay? Because it's up off the ground right here, you see that? Height, okay? And this time, my spring is outside the system. The spring is what's pushing that ball up, so I'm going to draw an arrow going into my system, okay, and that's the spring that is doing that. And that spring is what's making it go all the way up here and stopping. Now, once it gets up to the top and it stops, I still have no elastic potential energy. There's no thermal energy to speak of because I'm not dealing with friction. I'm not moving anymore, so there's no kinetic energy. So I'm all the way up at the top. So this is what happens. Okay? So I have the gravitational potential energy. Okay? So is this an open or a closed system, and how can you tell? Well, this is now an open system. Okay? It's an open system. And the reason I can tell is because energy comes in. Energy is added. Okay. If I wanted to think about it the same way I did up here, the spring isn't in the system. But the spring is part of what's going on, so it's not included, then that's a problem. Okay. This one says to write the mass to double check that your energies match up. Do you get the same number on both sides of the equal sign? So let's think about this. So our initial energies, so I'm going to just call this 25, 50, 75, 100. So I have 25, and our unit of energy is joules, so I'm going to put a J. Okay. I could also just do some percentages if I wanted to. I added some energy, okay, and it looks like I added 75 joules of energy. I didn't take energy away, so that's 0. And then over here in the final, I have all the energy, so 100 joules of energy. And 25 plus 75 is 100 joules, and 0 plus 100 is also 100 joules. So I did account for all of the energy. This is what makes it an open system. If you're going to put a number there, that's an open system. Okay. Now, there's several more examples here in this worksheet for you to work through, and you should do that. And then there's another page afterward. So go practice, ask questions if you need help, and I'll see you later. Bye.